So there we're talking about 1D, right? So what about in 3D, right? Because what we're really interested in is when we solve these conservation of mass. Conservation of momentum. As you'll see later, we write that equation over some volume of mass. So we want to know how a volume conserves momentum as it deforms. So we really need to know how to define the deformation of a volume in 3D. But of course, if we can track a line segment, or let's say if we can track any arbitrary line segment as something deforms, we can take 3 orthogonal line segments, create a volume with that, and then we can describe its deformation. So really what we're interested in is knowing how line segments change from one configuration to the other. Right? So we're going to define configurations. And I brought my little prop here, and I apologize I don't have a UT one. It's an old Boilermaker. I went to Purdue, so a little football here. So the idea is that we're going to define one configuration, and we'll call it the reference configuration. And after some deformation occurs, then we have another configuration that is the current configuration. And in each of these configurations, or at least in the reference, we have a little line segment ds. And I'm going to use a capital S, and I'm going to try to be judicious about putting the, because it's hard to tell the difference between a capital and a lowercase s, but I'll try to be judicious about putting little tick marks there. And so what we want to do is we want to track how this ds deforms or changes as it goes from one configuration to the other. Right? So in the deformed configuration, that same line segment may look like this. And so just to be clear, our reference configuration, okay, is relative. And sometimes you'll also see the terminology that this is called the undeformed configuration. And I put that in quotes because undeformed is relative, right? I mean, if we're talking about a steel casing, that you put in a wellbore, at some point that steel was iron ore in the ground, right? And then a little bit time later, it was an ingot of steel. And then, clearly it's been deformed a lot by the time it becomes a piece of steel casing. Of course, in a geomechanical setting, if you're talking about parts of the earth at reservoir depths, they've clearly been deformed by tectonic stresses over time. So when we talk about the reference configuration, we're talking about the sort of time t equals 0 at where we make the decision what time t equals 0 is. So at some point we say, okay, we're going to start tracking the deformation from here. This is the reference configuration. And so for my football, if I take it and this could be the undeformed configuration, and then I deform it over some time, and that's the deformed configuration, right? But also, I could make the deformed configuration my reference, and then I release the loads on it over time, and now this is my deformed configuration, right? Even though it's the same in a previous definition as my reference configuration. Right? So the reference configuration is the sort of the time t equal to 0 time configuration. Okay? So we want to track these line segments as they deform. And you'll also hear, again, Lagrangian for the reference configuration. And over here you might hear deformed. When I say here, I mean you might see this in literature. And you might hear me say it just out of habit. I'm going to really try hard to use reference and current, but you may hear me say undeformed or deformed just out of habit. And if you do, that's what I mean. So deformed, and of course this is also known as the Eulerian configuration. Okay? So just to be clear in my drawing here, these two line segments, you know, it's as if I took a marker and I drew a line on my football, right, and I deform it, right. The line is going to look different, but it's the same line I'm tracking through time.